we have talked about ground state of many electron atoms, helium and lithium to be more precise. Now we talk about the excited states. Why is it that we must talk about excited states? First of all, let us not forget that one of the beginnings of quantum mechanics is in spectroscopy, and spectroscopy involves transitions between ground and excited states. Secondly, well, maybe not secondly, another way of saying it is that all the color that we see all around us, right, we live in a colorful world, all the color that we see is because of transitions involving ground and excited states. And finally, it is not only color, but a lot of reactions that take place. The very fact that we see is something that involves excited state. Photosynthesis, something that we are all familiar with, involves excited state processes. So, it is not sufficient to restrict our discussion to ground states, we must understand excited states as well. Of course, building descriptions for excited states is much more complicated than ground states, but what we try to do in this course, our goals are not very high. We will be able to do it and get an idea of what exactly is done, right. And on a lighter note, we often do things better when we are excited. Same holds for atoms and molecules. Many times they do things better, whatever they are supposed to do, when they are excited by light, by absorbing light. So, that leads to all the photochemistry around us. So, let us not neglect excited state, let us learn how to study them. But before going there, what we have learned so far is about spin orbitals. Spin orbitals, okay, let me for once define a spin orbital, because I do not think I have said it so far. A spin orbital is a one electron wave function incorporating the spin part. Well, it is as simple as that, it is not rocket science, but it is important to not forget that an orbital is for the n plus 1th time a one electron wave function. A spin orbital, in addition to having the spatial coordinates for this one electron wave function, also has the spin part, right. So, for 2 electron systems we have learnt that we can have 4 spin functions, alpha 1 alpha 2 beta 1 beta 2, but we cannot have alpha 1 beta 2 and beta 1 alpha 2 by themselves, because we cannot distinguish between electron number 1 and electron number 2. So, we cannot say for sure that it is electron number 1 and not electron number 2 that has alpha spin. We cannot say for sure that it is electron number 2 and not electron number 1 that has beta spin. So, the best we can do is we can take linear combinations, and while taking linear combinations there is no reason why we should stick only to plus. A linear combination connecting the 2 terms by a minus sign is equally acceptable. So, we have to take that as well, and we have said that if you use exchange operator, just interchange the labels, then the wave function with plus is symmetric with respect to exchange, the wave function with minus is antisymmetric with respect to exchange. The reason why we worry about whether the functions are symmetric or antisymmetric with respect to exchange is Pauli principle or 6th postulate of quantum mechanics, which says that for fermions like electrons, the complete wave function of the system must be antisymmetric with respect to exchange. So, psi of 1 and 2 must be equal to minus psi 2 1. If you interchange the labels 1 and 2, the wave function must change sign. Okay. Great. So, what we are saying then is that if the 2 electrons in one s orbital had same spin, then we would end up getting the function psi s1 psi s2 psi 1 s1 psi 1 s2 multiplied by alpha 1 alpha 2, which gives us psi 1 1 2 would be equal to psi 2 1. It is not allowed. So, that is what leads to Pauli exclusion principle, and we have sort of taken this idea forward a little more by looking at Slater determinants of bigger atoms as well. This is where we stopped in the last module. Now, let us talk about the excited states of helium. Okay. So, let us start with an electron configuration. What is a state? A state, at least as a first approximation, is determined by the electron configuration. Okay. So, we are going to have some excited state corresponding to say 1s1 2s1 configuration. But as we will see, a particular configuration can give rise to different states, right, that we will see in a moment. But let us start. How do I write a wave function for a state with electron configuration 1s1 2s1? I can write 1s, then 1 in brackets multiplied by 2s, 2 in brackets. Okay. The problem is, what this implies once again is that it is electron number 1 in 1s orbital, electron number 2 in 2s orbital, and not vice versa. Who has told you that this is going to be the case? As we said earlier, electron numbers 1 and 2 are indistinguishable. 1 and 2 are labels that we are using to formulate the mathematical problem. So, if we just write 1s1 2s2, then our description would be incomplete. We must write 1s2 2s1 as well, and then as we have done in the earlier scenario, we have to take plus and minus combinations of these two wave functions. Okay. So, since we cannot say which is which, again this is becoming a cliche, we have to consider this wave function with a plus sign and also this wave function with a minus sign. So, right away you see that corresponding to a single electron configuration for helium excited state 1s1 2s1, I have generated two wave functions only while considering the spatial part. I have not even talked about spin yet. Only by spatial part I have constructed two wave functions, and it is not very difficult to see that the first one is symmetric and the second one is antisymmetric. Now, knowing Pauli principle, our job should be simple. We know that the total wave function has to be antisymmetric. Now, see, a symmetric function multiplied by another symmetric function gives you a symmetric function. An antisymmetric function multiplied by an antisymmetric function gives you a symmetric function. A symmetric function multiplied by an antisymmetric function or vice versa gives you an antisymmetric function. So, now see, in order to ensure that the total wave function is antisymmetric, the symmetric spatial part must be multiplied by an antisymmetric spin part. Yeah. Now, you might remember what the spin wave functions are for a 2 electron system. Remember we had said you can write alpha 1, alpha 2, or you can write beta 1, beta 2, you can write 1 by root 2 alpha 1 beta 2 plus beta 1 alpha 2, and you can write 1 by root 2 alpha 1 beta 2 minus beta 1 alpha 2. Great. Now, these three wave functions are symmetric with respect to exchange. This lone wave function is antisymmetric with respect to exchange, and here the spatial part is symmetric. So, in order to have an antisymmetric total wave function, it is imperative that the spin part has to be antisymmetric. Okay. So, the only choice we have for this spatial part is this alpha 1 beta 2 minus beta 1 alpha 2 function. This is called the S equal to 0 MS equal to 0 state. We will come to that shortly. But before that, let us see what happens for this spatial part where there is a minus sign. This itself is antisymmetric. So, we have to multiply it by one of the symmetric functions. We can multiply it by alpha 1 beta 1. No, what am I saying? we can multiply it by alpha 1 alpha 2 or beta 1 beta 2 or alpha 1 beta 2 plus beta 1 alpha 2 multiplied by 1 by root 2. All these 3 functions can be multiplied. Okay. So, what do you do? What do you get? From the symmetric spatial part, we generate a single wave function. From the antisymmetric part, however, since we have 3 symmetric spin parts, I will generate 3 wave functions by multiplying this single spatial part by one of the 3 different symmetric spin parts of the wave function. Okay? Right. And then this is going to be called the collection is called S equal to 1. The first one is called S equal to 1 ms equal to 1 state. Second one is S equal to 1 capital S equal to 1 capital M S equal to 0 state. Third one is called capital S equal to 1 capital M S equal to minus 1 state. What does all this mean? Well, before saying what all this means, let us have a look and let us see whether it rings a bell. I have 2 quantum numbers, A equal to 0, B equal to 0. Then the next one is A equal to 1 and for A equal to 1, B is equal to 0 and plus minus 1. Have you encountered this situation somewhere? Of course we have. Remember J and M rigid rotor, remember L and M hydrogen atom, same thing. When L equal to 0, ML has to be equal to 0. When L equal to 1, ML can be 0 plus 1 or minus 1. So, the same thing is there. So, what this capital S stands for really is the total angular momentum and capital MS stands for the Z component of this total angular momentum. Okay. Once again, this is a quantum mechanical phenomenon completely. However, as I told you, it is strange, but it is true that when you talk about spins, you can actually get most of the things done by using a very simple classical vector model, where you just draw the angular momentum as an arrow of appropriate length. So, how do I depict this S equal to 0 state? Well, first of all I draw this arrow up spin. Okay. Now, remember the angle, right, remember the angle, that angle is same for all electrons. Okay. Now, when electron number 1 has alpha spin, electron number 2 has to have beta spin and vice versa. Okay. We have to look at individual terms. So, how do I depict this individual first term? When electron number 1 has up spin, electron number 2 has down spin. Okay. And in order to get S equal to 0, S you can think is the vector sum of the angular momenta of the 2 spins. So, these 2 have to be disposed along a straight line. Yes. So, what I am saying is that if this is the angular momentum vector for electron number 1, this is the angular momentum vector for electron number 2. Do not forget that their phi values are not defined. Okay. In the classical picture, they are assumed to be precessing like this. Okay. I do not like to confuse students by invoking this precision business too much, but if you understand better, what I am saying is that it is both the up spin and the down spin of electron numbers 1 and 2 are actually delocalized over all possible values of phi, but then they are delocalized in a correlated manner, it is important to understand. Suppose you could freeze and measure, you would always find that the difference in phi's between the angular momentum vector of 1 and angular momentum of vector of 2 is 180 degrees. Okay. Suppose for this situation I take projections on the xy plane. Do not forget where the xy plane is. Draw something like this. This circle is in the xy plane. Suppose I drop a perpendicular, I draw a projection of the spin angular momentum of electron number 1 and I draw a projection of spin angular momentum of electron number 2. These two projections are going to be opposite in direction in the xy plane, that is what it means, okay. They cancel each other, okay. So, of course, if you take z components then also one is up one is down, they will cancel anyway. That is why s equal to 0, and if s equal to 0, what is ms? Ms is also equal to 0, because if the length of the arrow that you get by vector sum is 0, what will the z component be? It has to be 0 and nothing else. Next, let us look at this s equal to 1 business. Here the vector model is something like this. S equal to 1 means what? It means that the total length has to be 1, yeah, they have to add up. So, the first one alpha 1 alpha 2 is like this, beta 1 beta 2 is like this, alright. What would be the z component of this case? You have added 2, remember this length is root 3 by 2 and the z component is plus half. This length is root 3 by 2, z component is plus half. Half plus half, what do you get? You get plus 1. Of course, you might ask, if this is root 3 by 2, this is root 3 by 2, you just add them, you get root 3 and not 1. So, that problem is actually there, okay. But do not forget, this is a very qualitative classical picture, okay. But z component is easy to understand, z component is definitely going to be 1. In this case, it is not difficult to see that z component is going to be minus 1. Now, if you draw like this, then you will get some component along the x direction or whatever plane these two vectors are in, okay. So, s will still be equal to 1, but ms has to be 0, right, because the vector sum is going to be along say x axis or y axis or somewhere in the xy plane, z component will be 0. So, this is roughly, we have not really done the vector sum in very great detail, but roughly this is what the picture is. This is why you call them capital S equal to 0, capital S equal to 1 and so on and so forth. We are going to come back to this later on in a little more detailed manner, right. But for now we have, without saying it, learned a very very important concept. See, when the spatial part is symmetric, as we said earlier, the single antisymmetric part has to be multiplied by it to get the total wave function, okay. Since you get only one wave function for the spatial part, this is called the singlet wave function. The state described by it is called the singlet state. What about this? Here the spatial part has minus sign, fine, but you still have 1s and 2s orbitals. Does it matter whether electron number 2 or electron number 1 is in orbital 1 or orbital 1s or orbital 2s? It does not. So, this energy of this state where the sign here is minus is going to be exactly the same as the energy in this state, okay, unless you want to consider the energies of, unless you consider that there is interaction between spins and all that, that is not there. So, you do not have to worry about that. Just think of the spatial part, think of Schrodinger equation. If you could solve Schrodinger equation, here you have 1 electron in 1s, 1 electron in 2s orbital, same thing here, look at the configuration, they are the same. So, energies are same, okay. So, energies of these things are same, and then the energies of these 3 wave functions is definitely going to be the same, because the sign here is different from what it is here. Are we saying that the energy of singlet and triplet are same? Actually no. From whatever we have discussed so far, maybe you think the answer is yes, and from what I said. But one thing we have not mentioned so far is what is the effect of spin to be considered when talking about energy. For that, let me remind you of once again something that we have studied in high school. Remember Hund's maximum multiplicity rule states that have a greater multiplicity have a lower energy, everything else being the same. Here you see which one has greater multiplicity? This one has greater multiplicity. You might have studied multiplicity as 2s plus 1, and here that 2s plus 1, this is the s that you talk about. So, 2s plus 1 in this case is 1, 2s plus 1 in this case is 3, not very difficult to see, this is what you have learned. But what I am saying is that the singlet and triplet actually has got to do with the total number of wave functions associated with these states. For a singlet state where capital S equal to 0, you have only one single wave function. For a triplet state where capital S equal to 1, ms varies, you have 3 wave functions. That is why it is called triplet. And remember, triplet has a lower energy because of Hund's rule. It will suffice if we say that right now. It is actually a little more complicated than that, but right now we do not have to get into it. Alright. So, we have learned this very important concept of singlet and triplet states, and perhaps this takes our understanding a little beyond this 2s plus 1 business. Now, let us try to write the wave functions and let us see whether we can use our old friend Slater determinant to write the wave functions of the excited states. To start with, let us focus on one of the triplet wave functions. I start with this because the answer is simple, and since we are not doing it for the first time, we know already that the answer is going to be simple. The answer here is going to be more difficult because you see there are 2 terms, right. So, here I have 2 terms and I am multiplying it by another factor with 1 term. So, I am going to get 2 terms. Here I will get 4. So, let us start one by one. 1s1 2s2 minus 1s2 2s1 multiplied by alpha 1 alpha 2. We will have 4 terms, sorry we will have 2 terms. Each term will consist of 4 factors. Let us work out the first one, 1s1 2s2 alpha 1 alpha 2. Okay. So, we can write it as a determinant, is not it? We will write it as a determinant and we will write it in such a way that the determinant we write is going to be Slater determinant. So, what happens in Slater determinant? What changes when you go from left to right in a row? What changes when you go from top to bottom in a column? I hope you remember, in one case the label changes, in one case the spin orbital changes. So, let me write what will the 1 1 element be. The term I have is 1s1 2s2 alpha 1 alpha 2. So, we start with the lowest energy. So, we will write 1s1 alpha 1 here, and in the diagonally opposite one we will write 2s2 alpha 2. So, since we are going diagonal, your label as well as spin orbital both change. So, this is what we will write 1s1 alpha 1 2s2 alpha 2. What will I write here and what will I write here? What changes when you go from left to right in Slater determinant? What changes when you go from top to bottom? When you go from top to bottom, we write the same spin orbital, change the label. When you go from left to right, you change the spin orbital and keep the label. So, this is the Slater determinantal form of the wave function for the 3 1 state in which capital S equal to 3 and ms equal to 1. Now, I would like you to pause the video, work out the determinant for this one. Actually, I do not want you to pause the video. Without pausing, you should be able to tell me what the answer is. What would the answer be? Exactly the same treatment, right? Instead of alpha, we have to write beta. So, the answer is similar determinant. Wherever there is alpha, we write beta. That is your psi 3 minus 1 state. Wave function for the state in which capital S is 3, so triplet, and the z component of the angular momentum, total angular momentum is minus 1. Alright. Second one. Now, we are going to have not 2 but 4 terms. So, we are going to have to write a sum of 2 determinants. Okay. But then in every term we still have 4 factors. So, I can still write 2 by 2 determinants maybe. Let us see what we get if we try to write this as a sum or difference of 2 determinants. Now, I want you to pause the video really and see whether you can write it in such a way that you get a linear combination of two Slater determinants. Can you do it please? I hope you have done it. I hope you had stopped this video and you have done it, and let us see if you have got the right answer. This is the answer: 1s1 alpha 1 2s2 beta 2 minus 1s2 alpha 2 2s1 beta 1 plus half into 1s1 beta 1 2s1 alpha 1 1s2 beta 2 2s2 alpha 2. Slater determinant, right? When you go from left to right, you keep the label. When you go from top to bottom, you change the label. Okay? So, this is what you get for the triplet state. For the alpha alpha beta beta functions, you get Slater determinants. For the alpha beta plus beta alpha function, you get a sum of two Slater determinants. To conclude this discussion, let us see what we are going to write for the singlet wave function. As you see, the singlet wave function is almost identical. Well, almost identical is a little oxymoronic. The singlet wave function is very similar to the s equal to 1 ms equal to 0 wave function. What is the difference? The difference is, instead of plus here, there we had a minus, instead of minus here we had a plus, that is all. So, this will also be a linear combination of two determinants. This is what it is going to be. Please work out yourself. These things you can understand only when you practice by yourself. Now, let us compare the wave function for the 1 0 state to that of the 3 0 state. What do we get? Right? Why have I written 1 0? It is actually 0 0, sorry 0 0, psi 0 0 state and psi 3 0 state. Same Slater determinants. In the psi 0 0 case, you have a minus sign between them. In psi 3 0 case, you have a plus sign between them. That is what makes a difference. So, what we have managed to learn is that we can write spin orbital wave functions of multi-electron atoms as Slater determinants, or there it is better to say linear combinations, and this is an extremely useful way of writing wave functions, and it is also the starting point of more sophisticated treatments of multi-electron systems. So, that is what we are going to discuss now, and that is where we are going to enter the next phase of quantum mechanics, because all these interactions are going to make things so complicated that we have to invoke approximations. So far we have used approximations, but they have been very simple ones. Next we are going to talk about a little more rigorous applications. Again, rigorous application sounds strange. We are going to talk about more systematic, detailed, thorough approximation methods that are commonly used in quantum mechanics. We are going to talk about the variation method, and we are going to discuss perturbation theory. Somewhere down the line, if time permits, if it fits in, I really would like to talk a little more about angular momentum. Until then.